Hello everyone, welcome to COMP382, Theory of Automata. We are continuing our discussion about finite state automata, and in this video I'm going to talk about epsilon NFAs. Okay, finite, we have so far seen deterministic finite automata. We have talked about the non-deterministic ones that at each situation you might be in more than one state, and epsilon NFA actually is just an extension over NFA. In many textbooks they don't really distinguish between epsilon NFA and NFA. They just call all of them NFA. But in your textbook there is actually a separate section for epsilon NFA, so I thought it's better to keep it separate. So any finite state which has at least one transition which is labeled with epsilon, we call it an epsilon NFA. So what does this epsilon transition do? If you look at this finite state here, you can see that we have a transition from Q0 prime to Q0 which is labeled with epsilon. Having an epsilon transition between two states from here Q0 prime to Q0 just basically means that you are not using anything from the input. You can just don't touch the input, and using this transition move from Q0 prime to Q0. So basically just epsilon transitions, just inject the non-determinism into your finite state. It without any reading anything from the input, you can either stay at Q0 prime or move to Q0. Just think about it in this way. For example, look at the simulate of this string over this epsilon NFA that we have. The thing is, before we start, we look at Q0 prime and say that, okay, because I do have an epsilon transition, I can use that epsilon transitions and move to Q0. So instead of actually starting at one state, you can just think about it that I can start from Q0 or I can start from Q0 prime. Okay. From the Q0 prime, of course, there is no other transitions. So this one is going to stop. Someone actually might claim that you can still use the epsilon transition and move to Q0, but you can see that if you wanted to actually follow this path, this is going to be this path here. So we don't really need to follow this path. I can just ignore this one here. Just applying epsilon transition more than once here is not going to give me anything else. Sometimes it does, but in this case, in this finite state, we are not going to get more than this. So then from Q0, you see, you read a 1 from the input, and using a 1, you actually you stay at Q0 because of this transition. And by reading the 0 here, the next input, you can see that I have two transitions for 0. One will stay, one will move to Q1. So I will actually keep track of both of them. What would happen if I stay? What would happen if I move to Q1? If you stay at Q0, by reading the next one, you will actually need to stay at Q0. But if you move to Q1, from Q1 by reading a 1, you can move to Q2. So finally we accept the string in this epsilon NFA. Okay, so the definition of epsilon NFAs from your textbook is that any NFA that has at least one epsilon transition is going to be an epsilon NFA. The formal definition is very similar to NFA. We have again that 5 tuple, a finite set of states, an alphabet which is going to be a finite set of input symbols, a starting state, a set of accepting state, and the transition function. The main difference here is the transition function, that instead of only mapping from a state and the input symbols, it will actually include the epsilon in the transitions as well. everything else is going to be just like NFA. So let me actually show you a little bit more complicated example and see that how we actually simulate this string over this epsilon NFA. So let me show it to you. Okay, so you can actually say that we start from Q0 prime, right? I have an epsilon transition over Q0 prime, so I can say that using this epsilon transition, I can either stay at Q0 prime or move to Q0. But the thing is, instead of starting reading the inputs, you can actually just see that because there is another epsilon transitions over Q0, so by actually applying one more epsilon transitions, you get more possibilities here to as the starting point. So you can either start from Q0 prime, or you can say that stay at Q0 or move to Q3. Okay, it's just like I have 3 starting point here, and then read the applying the epsilon transitions more is not going to give me more possibilities here. If you actually look at this set, I have 3 possibilities as the starting states, right? If I keep applying the epsilon transitions, I'm not going to get anything more. I will actually just get Q0 prime, Q0, and Q3. The reason is that if you actually look at the epsilon transition, if you look at the finite state, the transition function, the transition diagram here, we are not going to have, for example, another epsilon transition over Q0 or over here. If we had, we could expand more, but we don't, so it's not going to give us anything more. So I can just stop applying the epsilon transitions, and then I can start reading the first input symbol. This is going to be 1, right? So from 1, I can, by reading the 1, Q0 prime doesn't have any transition over 1, right? So this path is going to stop. Q0 has a transition over 1 which stays at Q0. Q3 is going to actually has a transition over 1, so by reading a 1 from Q3 you can go to Q2. Okay, so what should I do now? At this situation, you wanted to read the next input symbol, but before reading the next input symbol, you should be careful that maybe applying the epsilon transitions are going to give you more possibilities, right? So apply the epsilon transition, and yes, here I do have more possibilities for Q0. Q0 with epsilon transition can either, you can say that, okay, stay at Q0 or move to Q3. And this one is also available, Q2 is also available. If you apply the epsilon transition again, you will see that I'm not going to get anything more than these 3 possibilities that I have here. So I would stop and then read the next input symbol, which is going to be 0. By applying the 0, if you apply the Q0, the 0 transition over Q0, you have 2 possibilities, right? You can either stay at Q0 or move to Q1 with 0 transition. From Q3, there is no transition over 0, so this path is going to stop. From Q2, there is no transition over 0, so this path is also going to stop. Okay, at this point, again, before reading the next input symbol, you have to try to apply the epsilon transitions. Maybe you get more possibilities, and yes, you do, because you have the Q0 here. So by applying the epsilon transition, you can either stay at Q0 or go to Q3, and Q1 is going to just be just like before, right? if you don't read anything from the input, so Q0 is still there. Now you can see that applying more epsilon transitions are not going to give you anything else. Then it is safe to read the next input symbol, which is going to be 1. So you will read 1. If you were at Q0, you would stay at Q0. If you are at Q3, you move to Q2. And if you are at Q1, you also move to Q2. Okay, so you are done with reading the input symbol, but the trick is still you have to apply the epsilon transitions, because it is possible that if you are at Q0, you can use the epsilon transition and move somewhere else, right? So even here, from Q0, you would apply the epsilon transition and say that, okay, it is possible that you stay at Q0 or move to Q1. So finally, then, at the end, which states you can be in, you can be either at Q0, Q2, or Q1. And because you can be at Q2, which is a final state, this is going to be accepted. This string is going to be accepted. But the main point that here I wanted to emphasize on is that when you are reading the input symbol, before starting and between reading any of the symbols, and actually at the end, basically I should say that before and after reading any input symbol, you should see that what would happen if you apply epsilon transitions. And not only one epsilon transition, basically, depending on your transition diagram, depending on your epsilon NFA, you might apply the epsilon transitions more than once. In this example, we just applied it once, but in some cases, you can actually apply it more than once. So I'm actually putting the closure here. This basically means that you are applying epsilon closure before and after reading every single input symbol from the input stream. So the thing is, when you are simulating a string, just assume that your string has n character, right? W1 through Wn. If you have an epsilon NFA, what you should do is that you should read something like this. Actually putting epsilon closure before and after all the characters. And don't forget the last one as well. So, because this is going to be kind of confusing at the end, how many times I have to actually apply the epsilon closure, this might actually be a source of confusion and error. To avoid that, one thing that we can do, which is going to simplify simulation, not only here for not only the simulation, but also later on during our proofs, we will see that this epsilon closure thing that we call it and show it using eClose, is going to help us a lot. You can draw your state table, the transition table, and in addition to all your input symbols, I'm going to actually add one more column and label it with label it with epsilon, and this column is going to show me eClose or epsilon closure, which basically means that if I apply epsilon closure, if I apply epsilon more than once, basically infinite times, where I can be if I start at state Q0 prime, if I start at state Q0, at state Q1, Q2, or Q3. For all of the states, you calculate the eClose, which basically means that, again, I'm repeating it. If I am at a specific state Q, if I apply infinite number of epsilon transitions, where else I can be. So in this finite state that I have, you can see that if you are at Q0 prime, if you apply epsilon transition once, you can see that you can be at Q0 prime or at Q0, so two states. If you apply epsilon transition twice, it gives you Q0 prime, Q0, and Q3. If you apply epsilon transition 3 times, you will again still get Q0 prime, Q0, and Q3. Nothing more. So you would stop. You would say that, okay, the equivalence for Q0 prime is going to be Q0 prime, Q0, and Q3. It just tells you that if I don't read anything from the input, where else I can be? If I am at Q0 prime, it means that I can be also at Q0 and I can be also at Q3. Similarly, calculate it for Q0. If you are at Q0, you can be also at Q3 without reading anything from the input, but you cannot actually be in any other states. So equivalence for Q0 is going to be Q0 and Q3. Equivalence for Q1 is going to be only Q1. The reason is that we don't have any epsilon transition to Q1, and it just means that if you are at Q1, nowhere else you can be without reading any input symbol. Similarly for Q2 and Q3, the equivalence is going to be only those states themselves. So be careful. The equivalence for every state is going to include that state. So let's do some exercise here over this finite automaton. What is going to be the equivalence for all the states? For Q0, the equivalence is going to be Q0 because of this epsilon transition, Q1 as well, because of this epsilon transition, Q2 as well, but nothing else can be added. So this one is going to be Q0, Q1, Q2. For Q1, because of this epsilon transition, it's going to be Q1 and Q2. For Q2, we don't have any epsilon transition, so it's going to be only Q2. For Q3, there is no epsilon transition, so it's going to be Q3. So this is going to be equivalence. Okay, the extension of the delta the transition function, or we call it deltahat, is very similar to the extension of the transition function for the NFA. The thing is, here when we are writing that deltahat Q0, for example, or any state, doesn't really matter which state you put here, and a string, it just means that if you read this string starting from this state, where you are going to end up. And it can be more than one state, right? Because this is going to be an epsilon NFA. This is going to be a non-deterministic finite state. The main difference in calculating the epsilon transition is that you should be careful that because you have a full string, you should just apply that epsilon closure between all of the input tokens to get the correct answer. Here is that just epsilon closure. Okay, so now let me, again show you the simulation of that string, this string 101 that we have done. Actually, I think we have seen it in the previous example. This is exactly the same example, right? Here, instead of always be careful and, be worried that how many epsilon transition I am applying, calculating the equivalence is going to just simplify life for you. Whenever you have an epsilon transition, before doing anything, calculate this column, calculate the equivalence for all the states. Then, when you start reading the input string, in fact, you are applying the epsilon transition before and after every token, right? So at first, you start from Q0 prime, but in fact, you apply the epsilon transition and you say that I would start from either Q0 or Q3 or Q0 prime. And here is actually the epsilon closure that tells you. You don't need to count how many times I need to apply the epsilon transition. Just directly look at the column equivalence in your transition table and just apply all of those states. So directly I know that if I am at Q0 prime, I can be either at Q0, Q3, or Q0 prime. And then, safely, without being worried about how many times you are applying the epsilon transition, now you can read the first input. This is going to be 1, right? Apply the transition over 1 over all of these states. Then again, apply the epsilon transition, which means that for each of these states that you have, you just need to look at the equivalence for them, right? And here, and expand them. So if you, because you have Q0 because of the equivalence for Q0, it means that you can be at Q0 and Q3. So I don't need to be worried how many times I am applying the epsilon transition. And because you have at Q2 and the equivalence tells you only Q2, you don't expand this one more than this. Then read the next token, then again apply the epsilon closure and continue until at the end, and never forget the last epsilon closure. Okay. So the language for epsilon NFA, just like for the NFA and DFA, the language of an epsilon NFA is going to be all the strings that will be accepted by your epsilon NFA, right? Which is going to be all those strings that you can find at least one path that ends up to one of the final states. So the last topic that I'm going to discuss here is the equivalency of DFA, NFA, and epsilon NFA. Although epsilon transition looks very fancy, and you might actually thought that, okay, maybe epsilon NFA is going to have more power than DFA or NFA, but no, epsilon transitions are not going to really give you more power, more computational power. Epsilon transitions are going to basically just makes designing a finite state easier. Just like, NFA and DFA, which are going to have exactly the same computational power and the same expressive, equally expressive, epsilon NFA is going to be equivalent to NFA and DFA. If you can create a finite state, if you can create an epsilon NFA for a language, you can also create a DFA for that. You can also create an NFA for that. So basically the theorem that we have to prove here is, because we have already shown that NFA and DFA are equivalent here, that's going to be enough if we show that epsilon NFA is equivalent to DFA or it is equivalent to NFA. So every NFA is also an epsilon NFA. Every DFA is also an epsilon NFA, right? So the main thing that we need to prove is that is every epsilon NFA, can we convert any epsilon NFA to a DFA or an NFA? Can we remove the epsilon transition from a finite state and still it actually accepts the same language? And the answer is yes. Just like the way that I showed you how we can create an equivalent deterministic finite state from a non-deterministic one, I can actually just show you that how we can create an equivalent DFA for an epsilon NFA. Basically, the procedure for creating equivalent DFA for an NFA is just like, from the epsilon NFA is just like what we did for the NFA. You just try to keep track of all possible states that you can be in, and for each one you will create one state in your DFA. I didn't actually show it through the slides here, but I can do the example for you. And then I will, in addition to this, I'm going to show you that how we can convert epsilon NFA to NFA. I think this one is going to be more interesting. So the slides are going to cover the how to convert epsilon NFA to NFA, but I will show you how to convert epsilon NFA to DFA as well. So what you are doing here is that, again, I will try to keep track of which states I can be. If I start from Q0 in my epsilon NFA, where I can be in general. So the whole idea is that you apply the epsilon closure over your state. For example, here it's going to be Q0. So again, I'm telling you, whenever you have an epsilon NFA, before doing anything, calculate the epsilon closure or E-close for all of the states. So if I am at Q0, basically it means that I can be at Q0, Q1, and Q2. So the starting state in your DFA basically is going to be Q0, Q1, and Q2. So I'm going to have one state for Q0, Q1, Q2 in my DFA. This is going to be the equivalent DFA. Then I'm trying to actually add all of the possible transitions. The first transition is going to be 0, for example. I have a binary alphabet, so I should consider 0 and 1. The transition over 1, when you are at Q0 and reading the transition 0, it's just moving you to Q0, right? If you are at Q1 and you have a 0 transition, you can actually move to Q1, or because of this transition, you can go to Q2, right? And if you are at Q2, if I read the transition 0, I will stay at Q2. Okay? But again, before I go and apply and say that, okay, the transition over 0 of this state is going to stay, I need to apply the epsilon closure again. So to see that where else I can be if I am at any of these states. So you can be at Q0, Q1, Q2, right? Because of the Q0. If you are at Q1, you can be at Q1 and Q2. If you are at Q2, you can be only at Q2. And if you are at Q2, you can be only at Q2. So basically from this state, if you are at Q0, Q1, or Q2, you can be at Q0, Q1, Q2. Nowhere else. You can see that this is just a repetition of those states. So the transition that I'm adding here over this state in my DFA over the transition 0 is going to stay at the same state, Q0, Q1, Q2, the state that labeled as Q0, Q1, Q2. So, okay. Let me actually I wanted to erase this part. Okay, now I'm going to check the transition for 1. What would happen if I am at Q0, Q1, Q2, and if I see a 1? If you are at Q0 and see a 1, there is no transition over Q0, right? So this one is going to stop. If you are at Q1 and you see a transition 1, you can go to Q0, you can go to Q3, right? If you are at Q2 and you see a 1, you can stay at Q2. Okay, again, before I go and add a transition for a state named Q0, Q3, Q2, I have to apply the epsilon closure. So epsilon closure over Q0 is going to end up to Q0, Q1, Q2, right? From Q3, it's going to be Q3, Q2 is going to be Q2. Okay, now I can see that if I apply the transition 1, over this state, in my DFA, I need to create a new state, and that state is going to be labeled as Q0, Q1, Q2, and Q3. You can see that I have all of these here. So I'm going to create a new state, and okay, I will continue. Now I need to count all of the transitions for this new state. Let me erase this one. Okay, so if I am at Q0, Q1, Q2, Q3, if I apply, sorry, let me label this transition. This is going to be a one transition. If I read a 0, where I can go? You can actually go to Q0, right? If you read a 0 at Q1, you will stay at Q1 or you move to Q2. If you are at Q2 and you see a 0, you would move, you will stay at Q2. And if you see a 0 at Q3, there is no transition, so this one is not going to go anywhere. But before going anywhere, you have to apply the epsilon closure again here. So Q0, Q1, Q2. This one is going to be Q1, Q2. This one is Q2. This one is Q2. So these are going to be the set of all possible states that you can be, which is going to be Q0, Q1, and Q2, which means that in your DFA, from this state, you have to move to this state with the transition 0. Okay, so now I can actually try to check the last transition, which is going to be transition 1 over all of these states. Transition 1 over this state is going to there's no transition 1 over Q0. There is 2 transition 1s over Q1, which one of them is going to Q0, another one go to Q3. Q2 with the transition 1 is going to stay at Q2, and Q3 is not going to go anywhere. Before creating a state with this name, you need to apply the epsilon closure. Okay, so if you are at Q0, you can be at Q1, you can be at Q2. If you are at Q3, you can be only at Q3. If you are at Q2, you can be only at Q2. So now you can see that this is going to be all the states that you can be in your epsilon NFA, which means that you have to add a transition 1 that goes to the same state. But before we leave, this one is going to be the starting state. Which states are going to be final state? All the states which has at least one of the final state in your epsilon NFA. So this one is going to be an accepting state. Also, this one is going to be an accepting state. Okay, so this is going to be your DFA. Okay, now I'm going to show you how to create an NFA from the epsilon NFA. This was our DFA. Now I'm going to show you how to create an NFA. This procedure was kind of fun, for the sake of proving that theorem that epsilon NFA, NFA, and DFA are equivalent. We don't really need to do it, but I thought it's kind of interesting, so I thought that's going to worth it to check. So if you are converting your epsilon NFA to NFA, it just means that you wanted to create a non-deterministic finite state, but you just want to remove those epsilon transitions. I don't want to have epsilon transition. Okay, what I'm doing is that, unlike DFA, here we don't actually need to keep track of all the possibilities and creating the states based on where we can be and those kind of actual discussion. In your equivalent NFA, all the states are going to be the same state as you have in your original epsilon NFA. So I will have a state Q0, Q1, Q2, and Q3. This is going to be the first state. The starting state is going to be Q0. Okay. but the thing is, for removing the epsilon transitions, I probably need to add more transitions. Okay, the main thing that's going to change here is the transitions are going to change over the epsilon. All the states are going to be the same, but the transitions will be different. We will have more transitions. Not only that, the accepting states are going to be more. So in your epsilon NFA, if you are at, so if you have only one, so for example here, if you have Q2 as your accepting state, it means that any string that ends up to Q2 is going to be accepted, right? But because of the epsilon transition, basically means that if a string end up to Q1, this string is going to be accepted as well. Why? Because this epsilon transition is going to move it to Q2. So in my equivalent NFA, not only I will mark Q2 as an accepting state, but also I will mark Q1 as an accepting state. And not only Q1, here I have to actually mark Q0 as well. Basically, you should check the epsilon closure that you have calculated, and for all of the states that Q2, which is an accepting state, is a part of the E closure for that state, those states are going to be marked as accepting state as well. Here, if you check this column, the epsilon closure, you will see that Q2 is here, Q2 appeared here, and Q2 appeared here. So all of these states, Q2, Q1, and Q0, all of them are going to be marked as an accepting state. The reason, again, is that in your original epsilon NFA, if a string end up to, for example, Q1, it can ends up to Q0 as well, right? Because of the epsilon transition. If a string ends up to Q0, it can also ends up to Q2 as well because of these epsilon transitions. So this is the way that we recognize the accepting state. Calculate the E closure and look for the accepting states in the E close of all of the states. Wherever you see it, all of those states are going to be marked as accepting state. Here Q0, Q1, and Q2. So we have 3 accepting states. Now we are going to add the transitions. Okay, adding the transition. To actually add the transitions, what I am going to do here is that I will start from the starting state and just try to simulate that, see that if I see a 0, where I can actually be in the original epsilon NFA, and based on that, add all the epsilon transitions into the equivalent NFA. So here you can see that Q0 has a direct direct 0 transition over Q0. So this is going to be 1 transition. But the thing is, when you are at Q0, before reading, basically I should probably explain it in this way, before even adding this transition, think about it in this way. You are at Q0, right? Before applying the 0 transition, apply the epsilon closure. So because of the epsilon closure, I can be at Q0, I can be at Q1, and I can be at Q2, right? Then apply the direct transition of 0. So Q0 is going to stay at Q0, Q1 is going to stay at Q1, right? And actually move to Q2 as well. And the state Q2 is going to, with the transition over 0, is going to stay at Q2. Then, not only that, apply the epsilon transition after that as well. So Q0, Q1, Q2, this one is going to be Q2 and Q1. And so basically here from, I mean, I'm not just skipping the details here, but here you can see that from Q0, by just reading one token 0, you can move to Q0, you can move to Q1, or you can move to Q2. So not only this transition is going to be added, one transition to Q1 is going to be added, one transition to Q2 is going to be added. Okay, so now I can safely say that, okay, I don't need to be worried about the transition 0 over the state Q0 in this new NFA that I'm creating. You would need to do exactly the same for the transition of 1. So let me actually just clean up here and do exactly the same for the transition of 1. So if I'm going to show it to you, here you can see that this is the full set of the transitions that we had. So again, for the transition 1, for the state Q0, first apply the epsilon transition. So it's going to be Q0, Q1, Q2. Then apply the 1 directly. So Q0 doesn't have any transition. Q1 has Q0, Q2, right? Sorry, Q0 and Q3, not Q2. And Q2 is going to have Q2. Then before leave, just apply the epsilon closure again. So this one is going to be Q0, Q1, and Q2. This one is going to stay at Q3, and this one is going to stay at Q2. So by checking all of these states, it's telling me that I need to have a transition from Q0 to Q0, one transition from Q0 to Q1, one transition from Q0 to Q2, and one transition, sorry, not this one. One transition from Q0 to Q3 as well. All of them marked with 1. Okay, because if you start from Q0 in your original epsilon NFA, by reading only one, you can end up to all of these states. Okay, so I need to add a transition for all of those states in my equivalent NFA. So now I am done with Q0. Okay, do exactly the same for Q1. Apply the epsilon closure. So it's going to be Q1, Q2. Then read, for example, the transition 0. Q1 is going to go to Q1, Q2. Q2 is going to Q2. Then apply the epsilon closure again. Q1, Q2, Q2, and Q2. Okay, so basically it means that if you are at Q1, by reading 1, you can go to Q1 or you can go to Q2. So this is going to be one transition here. Sorry, the transition over a 0. And this is going to be one transition here, which has been showing. Here is the final result for Q1 and the transitions over 0. Okay, similarly, I can check the transition 1 over Q1. Epsilon transition. Then the direct transition 1. So here is 1. Here is another one. Sorry, here is the second one. This is going to be Q3. And here is the last one. Then apply the epsilon transition. Q0, Q1, Q2, This is going to be Q3. This is going to be Q2. Okay, so just basically means that you have to go from Q0 to Q3. You have to go from Q0 to Q1 to Q0. You have to have a transition to itself. You have to have a transition to Q2. So these are going to be all the transitions over all the transitions of, these are not all. Okay, this is going to be complete. I have added all the transition of 1 over Q1. Okay, similar to that, you can do it for Q2. For Q2, apply the epsilon transition. It's going to be only Q2, right? And then read the 0. So with 0, you only go to Q2. And if you apply the epsilon transition, it's going to be again Q2. So I do only have one transition of 0 over Q2. Apply the transition of Q2 with 1. Again, the epsilon transition is not going to give you anything more. The transition 1 is going to move you to Q2. Epsilon transition is going to still keep you at Q2. So I'm going to add one more transition here. So 0 and 1. Okay, for Q3, epsilon transition is going to move you to Q3. 0 transition from Q3 is going to move you nowhere. I don't have any transition for Q3. So no transition for Q3 over 0. Similarly, no transition over Q3 for 1. And this is going to be done. This is the final NFA that we have. Okay, so we are done with the discussion of epsilon NFA. We have shown that epsilon NFA, NFA, and DFA are equivalent. You can convert them to each other. Here I have one more example for you. You can check it out. Try to convert this epsilon NFA to a DFA. The solution is here. And this is going to finish the chapter 2. So read the sections 2.3, 2.4, and 2.5.